Okay, is there anybody who is having trouble remembering how to do this? Cool, thank you for honesty, appreciate it. So basically there's a couple of things. One of the ways that I teach this in middle school, like back in the old days when I used to teach in middle school, I'd love to get back there again, but one day, anyway. If you think about this for a moment, because we're multiplying, you can actually set this up like an area, okay? And you can treat it like you've got an X and a 3 at the top, you've got an X and a -1 on the side, and you find the area of each of those sections, okay? So X times X is X squared, X times 3 is 3X, X times -1 is -1X, and -1 times 3 is -3. And so all I'm doing is just find the area of each of the little squares and then putting them all together. That's one way to do it. Okay, and sometimes people are taught that way. Sometimes people are taught what's called the FOIL method. Okay, FOIL stands for firsts, outside, I don't know why I wrote no, because it's already there. Outside, inside, last is what those stand for. And if you think about what that means, first means you're multiplying the first two terms in each bracket, then you're multiplying the outside two terms, so X and -1, and then the inside terms, and then the last two terms. So that's what we call the FOIL method of doing it. So that's another way that can be used to expand it. And so if I write it out like, so if I multiply the firsts, basically it's going to be X times X, etc. The third way that you can be taught is what I want to show now, because I'm going to use this later on in this unit, okay, this process. So I'm going to do it by, we know that when we expand brackets, we have to multiply everything on outside by everything inside, right? So we can write it as X, we can write it as the first term, X, multiplied by that set of brackets. And then we've got +3 multiplied by that set of brackets. So we've got the X times both of those and the 3 times both of those. Okay, now, you may not have been taught that process of expanding. I'm just using it because it's going to become useful later for me, right, for what I'm going to try to show you. And then if I keep going, X squared minus X plus 3X minus 3. Okay, so we just multiply the brackets out like you've been doing a number of times, and that simplifies to being X squared plus 2X minus 3. And some of you are going straight to that answer. And if that's the case, yippee, awesome, that's what I want you to do, right? Okay? Awesome. If you need me to go through any of these, you need to tell me. I'm just putting the answers up right now. I've gone through different ways to do it, right? And you can choose. By the way, there is another method that you could, some of I saw writing down. The crab claw method, right? Looks like a crab's claw when you do it. Who does that? Cool, that's fine, awesome. Okay, and if you think about the crab claw method, yeah, it's exactly the same as FOIL, just with a picture rather than letters. So if you think about crab claw, the first part of the thing we draw is the first, which is X times X. And then we're going X times -1, so that's basically this here, all right, which is those two expanded. And then we've got 3 times X and 3 times -1. So they're all the same, they're all related to each other. They're just different ways of expressing the same thing, okay? The last example, so the way I do this in my head is I know the process, so I'm going to times 5 by 7 and get 35x squared. And then I've got 5 times 1 plus 2 times 7. So 5 times 1 is 5, 2 times 7 is 14, 5 plus 14 is 19. And then 2 ones are 2. And we get those expansions. Okay? Now, before I move to the next step, as I said, you were taught this in year 9. But it's been literally 12 months since you've seen it. What I want to, well, before I move, is that okay? Has that come back to you and you think, oh yeah, I could do it? Do you reckon you could do that yourself now? Yes, no, maybe, a push, yep, if you maybe, no behind the back. All right. Okay, cool. So I just want to make sure that that was okay before we move on to new stuff, because we're going to use this to do the new stuff, right? So what we're going to be focusing on today is something called the Null Factor Law. Okay, the Null Factor Law. You're going to, those of you who are choosing to go on into methods, and even in a little bit in general, because it applies in some areas, this idea, the Null Factor Law, okay, will raise its ugly head a lot. So let's look at what it actually says, and then we'll look at how we actually use it. Now, before we do that, let's backtrack a little bit and talk about the things that we talked about last lesson. So last time we were together, we were drawing those parabolas, right? And we used a table of values and you plotted some points and you got graphs that look like this. Okay, so let's quickly review this stuff. So, talk to me about these 2 points here. They're called the roots. What are the other names for those? What else do we call the roots of a parabola? X-intercepts. Yes. Why? Because where are they? On the x-axis. When they're on the x-axis, what does y equal? 0. Okay, keep that in mind, please. Lock that little piece of information away for a few minutes. Okay, on the x-axis, y equals 0. Cool. All right, we've also got this little bit at the bottom, which is called the vertex. What else do we call it? What are the other names for it? There's a number of them. 2. Turning point, and what else? And stationary point. Well done. Stationary point. Okay? Year 11 name is the stationary point. Year 10 we call it turning point. Why? God knows. Because we're going to go with stationary point. Okay? But the vertex of the curve. Okay? Now this particular graph, what do we call this particular graph? There's two types of parabolas. No, not negative. This is an example of what? As opposed to that. Happy and sad. What do we call? Okay, so let's talk about the happy one first. Right? What do we call that type of parabola? A minimum. Well done. It's a minimum. Does that ring a bell? Yeah, because it goes to the lowest y value, minimum. Therefore, the other one is a maximum. Okay? So we've got our pieces of information to remind ourselves. Now I'm going to focus, what we're going to be focusing in on, right, for this particular lesson and tomorrow and then into the next term, we're going to really focus in on this idea of the roots. We're really going to hammer in on those. Why? Because once we identify the roots, everything, well, the axis of symmetry is exactly halfway between them, so that makes that easy, right? We can find that simply, right? Y-intercept is the easiest thing to find in the world because just let x equal 0 and there's your y-intercept, so that's a piece of cake. So the difficult ones are the roots, so we're going to focus in on that, okay? So we're going to talk about this idea of the null factor law. Okay, so the null factor law says that if you have a product, what does the word product mean? Multiply, yeah. So if I'm multiplying things, so what factors are things that are multiplied together, right? So if you have a product of 2 or more factors is equal to 0, which is where the null means 0, so that's where the null factor law comes from, null means 0, then at least one of the factors must be equal to 0. So let's think about what that actually means before we talk about why it's useful. Okay, so if I have 2 factors, A multiplied by B, right, 2 numbers multiplied together, A and B, I don't know what they are, right? But they're multiplied, so they must be factors. And if I let that equal 0, the null factor law says that either A must be 0, right? Or B must be 0, or they're both 0. Does that make sense? Yeah? So if A is 0, then it doesn't matter. 0 multiplied by who gives a rat's what b is. 0 times anything is 0. Right? So either a is 0 or b equals 0. So we've got a multiplied by 0. Well, we know that's 0 as well. So if the solution, if the answer is equal to 0, either one of or the other one must be equal to 0. Or they're both equal to 0. Because 0 times 0 is still 0. Okay? Now you're probably thinking to yourself, yeah, so, big deal. How is that useful? Well, it's really useful when we want to find the roots. Okay? Now, where do the roots occur? No, not when the other one, when what equals 0. When y equals 0. Right? Now, in a quadratic, in a parabola, where does the y appear? In the equation. So what does a general form of a quadratic equation look like? Do you remember? Y equals, good, equals, good. What? Good. AX what? Squared, because it's a parabola, so it has to be squared, plus BX plus C. Cool? So that's a quadratic equation there, right? Now, if we let that equal 0, if we let y equal 0, the x values must be the roots. Because if you think about it the other way around, if I substituted in an x value here and it equals 0, that must be an x-intercept because y equals 0. On the x-axis, y equals 0. This is what we tried to do with our linear equations last term, as in this term, right? We want to find out x-intercepts, we let y equal 0, and we solve for x. So in a linear equation, for example, if I have this, 4x plus 1. We recognise that equation. Does that look familiar to you? Reasonably okay. What kind of equation is that? 4x plus 1, what's that? It's a line, right? Yeah, God help me, it's a line. We literally just did a whole term on it. It's a line, right? So if I was to graph that, and I wanted to find my x and y intercepts. Okay, so let's find my y-intercept first. How do I find y-intercepts, ladies and gentlemen? X equals 0. Okay, so what happens when x equals 0 in this equation? Y is equal to 1. Thank you, Amy. Are we okay with that? When x equals 0, I've got y is equal to 4 lots of 0 plus 1, which is 1. So my y-intercept is at 1. Funnily enough, same as that number there. Nothing is new. What if I want to find my x-intercepts? Y equals 0. Right, so we're going to have 0 equals 4x minus 1. Can you just quickly rearrange that for me and tell me what x equals? Do it in your head if you like. Fraction or decimal, I don't care which. 0.25, we happy with 0.25? Move the 1 across, divide both sides by 4, we get 0.25. So 0.25, let's say round about there. There's my line. Cool? Right, so we're able to solve that equation and find my x-intercept. What?
Why is the top on y equals 4x plus 1 and the other one is y equals 4x minus 1? Why did we change it?
I didn't mean to. Thank you for pointing that out to me. God, yes. Much better. Thank you for pointing it out. Were you worried? Speak up, please, right? If you see an error, and I didn't mean to, and I thank you for pointing it out, right? Please say something. It's only been like 8 months, people, right? Leaving January out, 8 months, right? Okay, so my apologies, negative 0.25, that makes it much better because it's a positive gradient. Ugh. Right, I was so fixated on what I was going to, I didn't concentrate on this one, so apologies. My point is this, when we wanted to find the y-intercept, that was pretty easy, we could do that, right? When I wanted to find the x-intercept, I let y equals 0, and I can rearrange that equation. I can solve for x, okay? Sometimes it's complicated, sometimes it's not. right? But the point is I can solve for it and I can get an answer and I can put it on the graph, right? When it comes to a quadratic, right, it's a little bit more complicated. So if I go back to those examples we were just looking at, so let's look at this one here, x squared plus 2x minus 3. So y equals x squared plus 2x minus 3. So let's go back to that. This is the one, that's this equation here, right? X squared plus 2x minus 3, right? So I come to you to that and I say, rightio, I want to find the y-intercept. I want to find the y-intercept. Okay? How do I do that? Substitute what? X equals 0. Nothing's different. So can you do that, please? On that equation, can you please put in the x equals 0 and tell me what the y-intercept is? Yeah. What'd you say, Carl? Else? -3? -3, no, yes. -3, yes. I know, that's the point. Y-intercepts are easy. It's meant to be. It's meant to be, trust me, it's meant to be easy. Right, so we put in our 0 values, 0 squared plus 2 lots of 0 minus 3. Basically, it's the term on the end, just like it was for the linear equation, right? Equals minus 3. That's easy, right? We can find the y-intercept really easily, okay? No dramas. But when it comes to this little baby, find the x-intercept. How do we find x-intercepts? Y equals 0, right? So I've got 0 equals x squared plus 2x minus 3. So just solve for x. Good luck with that, because I haven't taught you how yet. But my point is, and that's my point, I haven't actually taught you how yet, right? We're going to, but I haven't yet. But the point is, you look at that, like we did linear with a minute ago, you could just rearrange stuff because there was literally just one x. You're just trying to get one x by itself so you can move all the numbers away, right? But you look here, I've got 2 and one of them's squared, for goodness sake. How the heck do I do that, right? So we need to come up with a way of doing that. And the way that we do it is we need to learn how to factorise it. Now, we're going to learn how to factorise these not today, maybe, depending on how we go. Because we're doing quite well, it's only just after 2. We're doing pretty well at the moment. But we're going to learn how to factorise. So we need to learn how to factorise because once I get it factorised, I can then use our null factor law. So I'm going to teach you how the null factor law works and then we're going to step back one more step and go, well, how do I get to that point? How do I factorise? Okay? I think you're going to find it's a lot easier than you think it is. But we're going to take it step by step by step. Okay, so let's go back to our null factor law then. Okay, so what I've got here, so the null factor law allows us to find the roots or the x-intercepts in any polynomial function, including linear and quadratic functions. Now we don't need to do it for linear because we know how to solve a linear equation. We can rearrange it easily. We don't need to do it, but we could, right? We do, however, need to do it for quadratic functions. So let's learn what the null factor law looks like. So let's look at these examples here. Now you'll notice in every single case, the quadratic itself is factorised already. How do I know that? What is the, look at question number, oh, sorry about that. Look at question number 1. It'll catch up in a second. There we go. How do I know that's factorised? Yeah. Does that make sense? It's factorised. Compared to what I showed you before, x squared plus 2x minus 3 or whatever it was, there's no brackets anywhere. Right? Brackets are the big hint that you've probably already factorised. Okay? What are the 2 factors in this example, number 1? What are my 2 factors? X is one of them, and what's the other one? No? No? Sorry, was that you, Flynn? X plus 1, well done. How do I tell factors? What separates factors? No? Multiplication sign. How do I tell? Yes, times, which is what you said. Yep, right. But we're going to use the terminology. Multiplication signs separate factors. What separates terms? Plus or minus. Okay, the difference, yeah? So we're looking for factors. So my two factors are x and x plus 1. Okay, now if I want the product of those to equal 0, the null factor law says that either the first factor is 0 or the second factor is 0. Okay, if they're both 0, it kind of defeats the purpose of having a problem. Because I've got 0 times 0 equals 0, there isn't a problem. We walk away and go home and have some afternoon tea, right? So we very rarely use the both factors are equal 0 situation. But what we do use is either the first factor 0 or the second factor 0. So we identified that the first factor is equal to 0. Well, the first factor is just x. So x is 0. Or the second factor is equal to 0. So x plus 1 has to equal 0. What does that make x? Negative 1. Here's what I want you to do. With your laptop, all right, here's what I want you to do. Could you please jump into Desmos for me? We're just going to use it to graph this and show what I've talked about. Okay, so can you jump into your laptop, go into Desmos, okay, DESMOS, and we're going to put in here the equation we just typed in, but we're going to write y equals rather than 0 equals, right? X bracket x plus 1, close brackets. So go into Desmos. The function is y equals x times x plus 1. Yes, it's a parabola. I know, shocking. But I also want you to have a good close look at the roots of the equation. Where are they? Negative 1 and 0, which is what we just calculated. X was 0 or x equals negative 1. So what we've done is, if it's in factorised form, we can then let each factor equal 0 independently, and by solving that for x, we get the roots of the equation. Such an important piece of information for us math moving forward. Right? Let's look at our second example. X multiplied by x minus 5 equals 0. So what are my two factors? X and, sorry, Lachlan? X take 5. Right, so my two factors are x and x take 5. Right? So let's identify using the null factor law, either the first factor, which again in this case is just x, or x minus 5 equals 0. Now I want the x-intercepts, I want the roots, so I need to find what x is. Do you notice that our factors are just little linear equations? Right? They're just little linear equations, nice and simple. And we've spent a whole term rearranging linear equations for this very purpose, so that when you get to that, you go, oh, I can do that. Right? So if x minus 5 equals 0, what does x equal to? 5. Right, so go back to Desmos, put that function in, prove to yourself that the x equals 0 and x equals 5 are your roots. You can just adjust the previous one if you want, or you can put a whole new function in. It's completely up to you. 0 and 5. Pretty straightforward, yeah? Factors. Either of these factors. So I want to hone on the right terminology, okay? Remember, we haven't learned how to get to this point yet. What I want you to see here is the two values that you work out for x equals and x equals. When you graph that equation here, with that equals y, by the way, not 0, right? Y equals, you let y equals 0, gives me the x-intercepts, right? 0 and 5. So let's do the next one. Okay, let's keep working our way through this steadily, because this can't emphasize how important it is that we get this. That's why I'm doing it now. Okay, what are my two factors in question C? 2x and x take 4. So let them both equal 0. Whoops. Right, so either the first factor equals 0 or the second factor equals 0. So you do them individually. So if 2x equals 0, what's x equal to? 0. Right, and what will x equal here? 4. Again, if you wish to, chuck in the decimals, put your equation in, see what you get. What I would like you to try and do is work your way down that list. Okay, now, I don't want you to freak out when you get to the surds. I knew some of you hadn't seen them, and I just say the word and then I can see the panic rise, okay? But I don't want you to panic, okay? You don't need to do anything.
Panic, so just hit surds out. That was focus on panicking.
Alright, so just work, okay, do D to F to start with. What I want you to do, identify the two factors, really simple. Let them equal 0, work out what x is, and then put them into the graph and just make sure that what you got for x matches the roots. Okay? What? Yes, so do one or the other one. Remember, either A equals 0 or B. Right. Cool. Yep, now graph that and see what it looks like.
I forgot already.
You agree?
Yeah.
So nice one, think of it. Sam.
Like if you have it like that and then it substitute. Oh no. Yeah.
James is that more than more than minimize how much you get. So it's 15. There's no what people are trying to do. Again, these questions are we do some other things like difference of two squares, perfect squares. Let's go. Is that good? Whoa, okay. No, the first one. So if you want to go to this one, you want to express how does this look? No.
Bring it just as a square root, so if it's square root, if 10 is the 3, just add the square root to the y. Alright, yeah. So plus square root greater than plus square root. Literally explaining that. I asked Larry It's actually really like trouble. I would prefer to be
The factors have to equal 0, not the values for x. It's the null factor law, not the null factor law.
which are actually really bad.
You understand what I'm saying? No. Okay. It's okay. I'd rather clear this up now than we go 2 weeks down the track and we're still going, what?
There was an attribution pattern.
Yes, that's right. So you'll notice what I've tried to do here is I've done them in full, and I've done that deliberately. You may have gone straight to the last answer, I don't know. You might have done them in a slightly different order, but in the end it doesn't matter. So first of all, could you please confirm that you agree with what I've got for those who have finished? I know I went quickly, but they don't take long. Now, what you need to try and recall what we are trying to achieve. What we are trying to achieve right now is to go from the quadratic equation, which is the bit at the end, back to this. So we're trying to factorise and go from x, for example, we're trying to go from x squared plus 6x plus 8 back to the factorised form x plus 2x plus 4. Because once we've done that, we can then find the roots. Right? So that's what we're trying to do. So we're trying to go from x squared plus 6x plus 5 back to x plus 1x plus 5. We're trying to go from x squared minus 6x plus 8 back to x minus 2x minus 4. So we're looking at that pattern. How do I go from this at the end back to the factors? That's what we're trying to do. But in order for me to show you the pattern, we've just gone forwards. Right? So I've gone from the factors to the equation. What I want to do is look for the pattern to go the other way. So let's look at the very first equation. x plus 2, x plus 4, and I've got x squared plus 6x plus 8. So can you see any relationships between what we're trying to achieve, the 2 and the 4, really, right, and the final equation? Keep going, keep going. What are factors? Be more specific for me, Carlos. I'm going to come over here and write x squared plus 6x plus 8. Let's focus on this one, right? Remember, we were trying to get to here. We're trying to get to that, right? So talk to me. Good. So 2 and 4 are factors of 8. Right. Before we go any further, do everyone agree with what Carlos is saying there? Now, 2 and 4 are factors of 8. Yeah? Now, let's go back to the original expansion. How did we get the 8 in the first place? We times 2 and the 4 together, didn't we? So they're obviously factors of 8. But it's still an observation you had to make. Okay? So, that's the first observation, and that is a really key one. The numbers that we want in our factors are factors of the last number. Now, to be precise, they're actually factors of the 8 and the last number, but we're going to cross that bridge later. Okay, so let's come to that in a minute. So let's look at the 8. Factors are 2 and 4. So there's 2 and 4 there. What else do you observe? What else is there? You could, and I'll tell you why you don't in a minute, but let me write that up there, because the factors of 8 are 2 and 4 and 1 and 8. You are 100% correct. We're going to come back to why you don't choose the others in a second. When you say equal to, what do you have to do with them to get to the 6? You have to add them, and it's really important that. So the 2 and the 4, right? Look here. The 2 and the 4 add together to give 6. What do 1 and 8 not add to give? 6. So that's why you don't choose the 1 and 8. Because they have to, so the two numbers that we choose, the 2 and the 4, they have to do two things, right? They have to multiply to give that number and add to give that number. Because that's exactly what happened here. Have a look in the equation, the expansion. The 2 and the 4 had to add to give the middle term, 6, because 2x plus 4x gives me the 6x. And they multiplied, the 2 and the 4 multiplied to give 8. Now, does that pattern hold in the rest of the examples? Have a look. So look at example number 2. The two numbers we've got in our factors are positive 1 and positive 5. What do they add to give? 6. What does 1 times 5? 5. Okay. Does it work there? Let's try the next one. Now, let's go backwards slightly. Look at the 8. What are the factors of 8? We've already talked about that. 2 and 4 and? Ooh, don't use that number. 1 and 8. So the factors of 8, which is the end term, right? This term here. The factors are 2 and 4 and 1 and 8. Are we cool with that? Now, we have to organise those factors to equal negative 6. They also have to add to give negative 6. Right? Because the factors have to multiply to give the last number and add to give the middle number. That's the pattern we've found so far. Let's see if it continues. So, is 2 times 4 8? Yeah. But is 2 plus 4 negative 6? No. Okay. Let's try the other factors. Is 1 times 8 8? Yes, obviously it is. Is 1 plus 8 negative 6? Oh, bugger. Okay, so are there any other factors of 8 that we haven't accounted for? Very good. Very good. Negative 4 and negative 2. Is negative 4 times negative 2 positive 8? Yes, it is. And if I add negative 4 and negative 2, what do I get? Negative 6. And if you look in the answers, the factors, x negative 2, x negative 4. Mind blown. Okay, let's do the last one. This time we're looking for factors of negative 3. Okay, so what are the factors of negative 3? Well, 1 and 3, are they factors of negative 3? Okay, so negative 1 and 3 or 1 and negative 3. You call that? Which combination of those would I add together to give negative 2? That one? No, well, is negative 1 plus 3 negative 2? No, it doesn't. See, it only works once. Yep, it only works once. So they can't both be right, so it has to be one or the other. In this case, it's negative 3 and positive 1. And look at the factors. X, negative 3, x, positive 1. Okay, try for yourself. If I can get this thing to slide. Not that, ignore that. Try that one. Right? I want you to factorise that. X squared. That's what?
You go from being really nice and giving us nice numbers.
It is a nice number. So what factors are we looking for here? Factors of what? Positive 6. Okay, we're looking for factors of positive 6. This is the pattern that we discovered. Right? So what are my factors of 6? 3 and 2. What else? What are the other factors of 6? 1 and 6. Okay? But I can also get negative 3 and negative 2 and negative 1 and negative 6. Couldn't I? So which combination, or what do I do now? How do I choose, Leno? Why do I choose those two? To get negative 5. What do I have to do with the numbers to get negative 5? Plus them, add them. Yep. So I'm going to choose negative 3 and negative 2. What are my factors then? So now complete the question. What are my two factors? Yep. That's it.
Doesn't matter which way you put them.
Huh? Nope. No, because multiplication is commutative. Doesn't matter what order, as long as the sign's with the right number, doesn't matter if you put which order you put them in. No. Yep. No. I don't know. Just try that. Let's try it. No, I'm not saying that's a question on the exam. I'm going to clear. I'm nowhere near writing the exam yet. Just got to write the last one. About 60 papers to mark this holidays. Try that one. No, don't call out, please. No, just give people a chance. What'd you get? Hey, you do things right more often than you give yourself credit for.
No, I can't think of it.
That's right. Right. Yes. Right, so what? So Rani just made a connection which is so important. No. Believe me, if you walk out of today with that connection, I've done my job. Right? The connection I want you to make from today is if I give you the equation y equals x squared plus 10x plus 21. right? If I give you that equation and say, I want you to tell me the roots of the equation. Where is that thing going to cross the x-axis? Right? You can walk out and go, rightio, well, I can't rearrange that because I've got to let it equal 0, so I need to factorise it. Okay? So I've learned to factorise this simple one. We're going to do more difficult ones as we go, but these are just the simple ones. The difficult ones have two extra steps in them, but they're not much more difficult. It's same processes, right? Once we factorise it, what do we do then to find the roots? Once I factorise, how do I find the roots?
Make them 0.
Let them equal 0 and solve. So what will be the roots of these two?
-7 and
There we go. -7 and -3. That's what today was all about. So, okay. Belle's going to go in a second.
I've done my job as a student now.
Okay. Now, I've given, up in the top, this is exercise 5C, right? Up in the top right, you'll see a selection from questions 4, 5, 6, and 7. Question 7, I've got some examples there. They are at the problem-solving end. I want you to realise that you actually can do those. Because if I want to cancel, what do I need to do? We can only cancel what? Common factors. So in order to cancel, you need to factorise. You've just learned, and I know you need more practice, that's obvious and important and given, right? But you could probably factorise that top line now. You need to think about what are my factors of 54? That I had to give -3. Factorise it, does anything cancel? Ding ding, right? So you can do those, but you have to factorise the top line or bottom line first. Right, so your job, and please don't let this go. I know you're about to go on holidays. I completely understand that. If you are here tomorrow, we are just going to practice this sort of stuff. I'm not going to go further. Okay? So if you're here tomorrow, we're going to practice factorising because if you want to be good at this, you just have to practice it and get it into your head. Okay? So there's some questions. If you're not going to be here tomorrow, could I please encourage you over the holidays to watch the video that I just created again on today's lesson, right? And then practice some of those questions. If I don't see you tomorrow, have a great break. I'll see you after the holidays. If I do see you tomorrow, I'll see you tomorrow.